Swayam Prabha. Digital India. Educated India.
Okay, good morning. We will now carry on with what you call as multi-core systems. But as we proceed towards multi-core system, what is important there? What is the difference between a single core system and a multi-core system from an organization point of view or from an architecture point of view? What is the new addition that we are going to get? When you look at a multi-core system, we will have several superscalar processors, several cores, let me call it C1, C2, C3 till Ck. Today K can be as big as 32. Okay. Now there are several, instead of one superscalar Tomasulo out of order branch predicted thing that we have seen, we would have 32 such. Now what in addition? So what should we learn in this multi-core? The most important thing is how all these things can work together. And the way they work together is by passing actually messages between them. One thing is, we can do a traditional thing like, I could have 32 different activities in your mobile phone, right? So you have 32, one mail server is running, one mail daemon is running, one WhatsApp daemon is running, one message SMS is running. So each one can be put onto one core and it will be just running there. And whenever it is awakened, you get a message, it will awaken, it will do some activities. So like that, several sequential applications, but instead of one CPU executing all these sequential applications, I will just distribute this workload across these 32 processors or 8 processors. This is one easiest way of doing. So what do you achieve by having a multi-core processor? I have several tasks, totally unrelated independent tasks like WhatsApp and Gmail will not talk to each other, okay, but they are two independent tasks. One, instead of both being time shared on a same CPU, I can push it across different CPUs and they can execute. So this is how multi-cores are utilized today. There are very few really parallel applications. What is parallel? Suppose I want to add 100 numbers, tell the program, right? You will always say for I equal to 1 to 100, S is equal to S plus A. Correct? That is an inherently sequential program. So if I ask, say, if I have 4 processors, take 25 numbers each, add them, then finally add the answer. That is a parallel way of looking at it. Right? We have seen that in SIMD. This SIMD type of thinking is going to be very less. Or the number of programs today that is running on your mobile phone which essentially exploits the multi-core facility there, it's very, very less. You are getting this? Because for several reasons, people do not know how to write parallel programs, people do not know and we do not have automatic parallelization environment, though we are talking for years together. So compilers may not have matured to that level, right? So there are a lot of issues by which I can't write parallel programs. So the trivial thing is that just go, and so what happens today, if I have a quad core, now 2 of the cores are like never wake them up, okay, they are sleeping eternally, right, and some 2 cores will be used in which one core would be some 60%, another will be 20-30%, right, the remaining core will be sleeping. So because we do not know how to use it. Now the best way of trying to use your mobile phone is develop a mobile app which will have some chess game with lot of artificial intelligence, which will start using these 4 cores, do some A star search or some AI based searching and try to utilize. So you have to write parallel programs to do it. I do not know whether Android actually has a multi-programming or parallel programming environment at all. You are able to appreciate it. Now so the main issue here is that if I have a multi-core system, I would like to, if I want to exploit the speed of this multi-core system, then I have to write parallel programs. I have to take one program, split it into concurrent parts which are concurrently executable, execute on these cores and get back the results, aggregate the results and hence see the speed up, okay. So I should develop the acumen of writing parallel programs. So towards the end of this course, I will spend 2 or 3 classes basically to teach you how to write some parallel programs, very interesting parallel programs, simple parallel programs. Okay. I will also introduce a new model of computation. You have already seen a model of computation in your data structures course, right? The algebraic model of computation, based on which you get your order notations. Now I will give you some parallel models of computation. I will also teach you that, so that makes this course very complete. Okay. Now when I write parallel programs, the way one program will talk to another program is through passing messages, and the way they pass message, there are many ways of passing messages. We will look at those message passing systems down, but one way by which your current ARM processors that you have on your chip and all process message is by between the cores is using the memory. So that is why we call it as a shared memory architecture. I share lot of memory across these C1 to CK. I share memory, and if I want one fellow, if C1 core 1 wants to send some result to core 2, how do? They write it into the memory. This fellow writes into the memory, that fellow reads from this memory, and vice versa. Correct? So we have to understand the memory management system in total before we start appreciating multi-core systems, okay? Because everything there centers around memory. We have learnt how to construct individual cores. We know how to construct them. When I want to integrate these cores and give one model saying there are k cores, use them, and this is how you can use them, and this is how you can analyze a program on them, this is how you can program them. Before we even go into that aspect, it is very fundamental for us to understand how the memory is organized, right? So in the next 3 to 4 classes, it is also aligned to your assembly language assignment, we will talk more about memory management, okay, fair enough. And then I will talk about how memory management is done on individual cores, and then extend it to how that could be how that is extendable for multi-core, okay. We will do those two things before we go into programming these multi-core processes, okay. Okay. So what are two types of memory? There are two types of memories. One is a non-volatile memory, and another is a volatile memory. What do you mean by non-volatile? When the power is switched off, the memory contents do not get erased. A volatile memory is when the power is switched off, when current is not passed, when electricity is not available, when power is not available, then what happens? Your memory gets erased. So this is the difference between a non-volatile memory and a volatile memory. Now let us say the non-volatile memory that we see today are the disks. There is something called erasable programmable read-only memory, EEPROM. These are all the non-volatile memory. The volatile memory are your RAM, your cache, your registers. Okay. So now you have something called what we call as the memory hierarchy. What we understand by this term memory hierarchy, I have the disk, from that I could load data into RAM, from RAM I can load data into caches, from cache I can load data to registers or access directly. So the volatility decreases So this is totally non-volatile, while the remaining things are volatile, but the speed actually again decreases. Registers are faster than cache access, caches are faster than RAM access, RAM is much faster than the disk access. Okay, got this? So when I am looking at a single processor or single core, whatever say C1, I have to understand the memory hierarchy from its perspective, right. From C1's perspective, what is the memory hierarchy? Once I understand the perspective from C1, sequence perspective the memory hierarchy, then I can basically start elaborating on that and take it to the other stages. So from an individual course point of view, what is the memory hierarchy? We will now start looking at it. Let us come from the bar. So there is a disk, right, and this fellow has a disk driver which is a software, right. If you insert a USB, driver is being installed, Windows will give you that command, right, this is what. And disk actually has a disk controller who understands how the disk works. Okay. This disk driver will be talking to the disk controller. Where will this disk driver execute? This will execute on your CPU. The disk controller will be a separate hardware and it will be executing. While this software will be used to program or talk to the disk controller, saying, hey, this is the data, write it, this is the data, read it, this is data, erase it, etc. And the disk controller will do internally, it will go and see whatever action which the the OS wants, it will get it done from. Okay. So this is running on the normal CPU. This is a software and that is a disk driver which actually programs the disk controller to do lot of activity on this physical disk. Correct. Now, how do you read or write into a disk? From a disk, I write it into a RAM. Okay. From the disk, I write data to the RAM or programs to the RAM, and as a CPU, I access only the RAM. I do not access the disk directly, because the way instructions are executed, it assumes that I have segmentation, you have already done, right. So I have to load it into the memory and use that, right. So the programming model that we have conceived of only will look at RAM, it will not look at disk. So you can't execute a program directly from the disk, it actually copies that program into the RAM and executes from the RAM, because that is very much necessary for all my intra-security, inter-security, so many things that we have talked of from a segmentation point of view. Okay. Now let us look at what is happening at the RAM level. When I am writing a program, I say I have a 32-bit architecture, right. That means I tell the programmer, I tell the compiler, you can address anywhere in this 32-bit. I am giving you a 4 GB address space, you can go and use this 4 GB address space. So every program is given a 4 GB address space and it can go and use it. But ultimately this 4 GB is given, this is called a logical address space, because physically it may not be present. Physically on your RAM, I may have only 2 GB. But I as a programmer can access anywhere in this 4 GB. I will be given 4 GB logical address space, but the actual RAM will be only 2 GB. Right. So as far as the architecture goes with respect to the programmer, I go and say I am giving you 4 GB irrespective of whatever I have. So that I may have 2 GB, I can have 128 KB, I could have 1 MB, whatever here physical memory, but I tell the user, I tell the programmer, hey, I am giving you 4 GB. So essentially that means I am telling the programmer, here is a virtual memory, you assume that you have 4 GB, that 4 GB is not physically present, it is virtually present to you, right. So I tell the programmer, you write the program, do not bother about anything about my physical RAM or anything. You just assume you have that entire 32-bit address space of 4 GB, write your program. I as an operating system with the support of the hardware will see that your 4 GB program will be executed with the small half a GB that I have. It is my responsibility to execute your 4 GB program on say half GB that I have. Are you able to follow? So essentially the architecture and the operating system together are presenting to the the user a 4 GB virtual address space that is not physically present. Why we call it as virtual? Because it is not physically present. It is not available in hardware. It is not available on the RAM. But the OS and the architecture tells the user, assume you do, I will take care. Okay? Are you appreciating this fact? And that is why it is called a virtual memory, because it is not physically available. All of you followed? Right. Now, in which strength is it saying? Suppose I go and say, oh, tomorrow morning I'll go, I'll jump from a helicopter, I'll do skydiving, right? Okay. There is no rationale behind that statement. I can't even climb 3 floors of ICSR. My head starts rounding. I go and say I'll jump from a helicopter tomorrow morning, I'll land directly in the 4th floor. It's meaningless. So there should be some rationale behind the operating system and the architecture trying to make such an assertive statement, right? What is that rationale? Are you getting this, right? So what is the rationale? What could be that rationale?
To avoid the overhead of copying from the disk.
Rationale for making that statement. You are saying what will be the consequence of this statement. Huh?
Entire program is not executing at the same time.
That is the rationale. So can you make it? Entire 4 GB need not be, every time 4 GB need not be there. So can you make that rationale bit more effective?
Only next instruction and data for the next instruction.
Exactly, that's the thing. If I ensure that at any point of time the next instruction to be executed and the data necessary for that next instruction to go to completion are available in the RAM, then eventually my program will lead to completion. I do not need all the 4 GB at any point of time. At every point of time I need the next instruction to be executed in the RAM so that I fetch it. I also need the data that is needed by the next instruction to go to completion. That also should be in the RAM, then only I can fetch the data. If this I ensure for every clock cycle of my entire program life, then I can essentially go. And that next instruction can be, assuming even it can be 1 KB next instruction, may not be 1000 bytes, okay. But even assuming it is 1 KB, I can execute this entire program using, including data, I can finish off in 1 KB in some sense, correct? Are you able to follow? So this is the rationale behind the virtual memory concept itself, saying I do not really care how much underlying memory I have. I should have something called RAM. I can't have 0 RAM, but I will have something called RAM. But if I have that something called RAM, I can go and execute program of any size. So as a 32-bit architecture, you can only write programs that is as large as 4 GB. Write that program with data, everything. Come to me, I'll execute and irrespective of what I have in my physically. The rationale again is that always during the lifetime of a process, at any point of time, the next instruction to be executed and the data needed by the next instruction to take it to completion should be available. If this is ensured across the life of the program, then essentially the program will go to completion. So this is the rationale behind what we call as virtual memory. Got it? Got it? Any doubts?
In instructions are executed in the pipeline, right? So like there might be a situation like multiple instructions may need the data at the same time.
But that's all taken care by your dynamic scheduling. Load store, now you are talking of a load store architecture. Somebody with 2 loads will come at the same point of time, let it come. But your that will be taken care by your dynamic scheduling. I will come to you. What I understand what you are talking of. Right? Okay. I'll come to you. There are multi-port reads and so many things. We'll certainly look at this in great detail. Okay. Right. Okay. First we will talk about virtual memory. What you are talking is about, we will resolve it at a cache level, and there are going to be some structural hazard and so many things are going to come. Then we will have split cache, multi-level cache. First we will finish this virtual memory, right. Are you able to appreciate this? Okay, chal. Now what happens is as follows. So how will I say? So there is something called a logical address space, and there is something called a physical address space. The logical address space is maintained in the disk. Your OS course will teach you how it is maintained in your disk. The logical address space runs between 0 to, in a 32-bit architecture it goes from 0 to 2 power 32 minus 1. All your segmentation, everything is done on this logical address space. So if I want memory, I have to give consecutive memory for a segment, all these things are done. The segment descriptor, everything is done in the logical address space. Your entire segmentation is in the logical address space. Okay. Then what you do, then there is some physical address space which is say 1/4 of its size. For example, let me say I have 1 GB memory. Okay. Now what happens is, what is my rationale? At every point of time the next instruction to be executed and data needed by the next instruction should be loaded into memory. I will not load instruction by instruction. Why should I not load instruction by instruction? I will not load instruction by instruction because when I want to access memory, how does the CPU access memory? Memory and all the peripherals are in a common bus. So I have to go and request for that bus. That bus fellow will bless me with the request. Then I become the owner of that bus, and then I go and read memory and get it back. After that I relinquish that ownership and then somebody else will become the owner. So if I want to read from memory, it is not a joke, it is a long drawn process, okay, right, you got it, it is a very long drawn process. So I have to request the bus arbiter, I have to get control over the bus, then I have to send request to the memory, then it will take its own sweet time because it is much slower than the processor. Then it basically sends the data back. I have to collect it at the CPU, then I have to do all these cache coherency, all these policies. I have to collect it, then I have to see all these policies, I have to see whether there is any segmentation violation, all these things I need to check, and then finally it comes up, okay, right. So every time I want to access data, there is a latency involved, right. So if your CPU wants to access data, there is a latency of tau involved, plus there is an access time. Access time is time to read 1 unit of data. So this tau is contributed by the bus. I ask the bus, "Arey Baba, give me some control," then the bus blesses me. That the time required to take the blessing of the bus will be this tau. After the tau only I will start accessing data. So the total time will be tau plus access time of memory. Read or write, access means read or write. So if I want to read from memory, I need some time that is given by this, or write into memory. Let us take this. So suppose I am doing n bits at a time, 1 by 1, this will be n into tau plus access time. But in one read itself I read n bits, then it will be tau times n into access time. I hide the latency. I hide the latency because one time I am asking for the memory, one time I am getting the request, I immediately transfer n units of data, right, rather than 1 by 1. So because of this reason, this latency is quite significant. It's not, it's not something which is neglectable, it is quite significant. So if I multiply that tau with n, then it goes back to my monkey example, right, it becomes a drunkard monkey bit by a scorpion. So the whole thing becomes extremely complex. So I would like to hide this latency, and that is why when I want to transfer data from the a slower device to a faster device, whether it be from disk to RAM or the RAM to cache, I do not transfer 1 byte, I transfer chunk of bytes. So, these devices like your RAM, your disk, your cache, they are all called block devices. What do you understand by the term block? Instead of reading 1 byte at a time, I read 1 block at a time. So, my basic granularity of trying to access these disks are basically a block. Your disk is also, your hard disk is also a block device. So, when I read from the hard disk, I do not read 1 byte, but essentially I read a set of bytes which can be as long as or as large as 4 KB or 8 KB, okay, right. So, since we are now talking of block devices, I will only move data in blocks. Motivated by this, I go and have this physical address space split into several blocks, namely 0, 1, 2, 3, etc. And each block from the virtual memory point of view, that is I am talking of the logical address space and physical address space, each block is called a page. Now, in the physical address space, this is the RAM. What happens? We split this RAM into equal parts, each part is equal to the page size, whatever page. So, similarly the logical address space will also be split into pages, each one is a page, okay. So, your program and everything will be in the logical address space. As and when required, it will be moved from the logical address space to the physical address space for execution purpose. Is it okay? Right? Okay. And the movement will not be as 1 byte after 1 byte, it will be moved in terms of pages. So, I will move, if at all I am moving something from a logical address space to the physical address space, the minimum granularity will be 1 page, at least 1 page I have to, and vice versa. I can't just move 1 byte or 2 byte, etc. Okay. So, I will between the logical address space and the physical address space, the movement will be in terms of 1 block of data, which I call it as page. So, in the RAM, the logical address space I have split like this into equal parts. The same equal part I can split the RAM also, so that a page from the logical address space can go and occupy this physical address space. So, the size of the page here in your logical address space is equal to the size of the page in the physical address space. So, these things like a photo sits inside a photo frame, right. If I have a photo frame, why do you call it as a photo frame? Because photo will eventually I can keep a photo inside, you can't go and sit inside that, only photo can sit. Similarly, a page sits inside a page frame, correct. So, all these things on the RAM are called page frames, onto which some page from the logical address space currently stored in the disk can come and occupy, okay. Do you get this? Are you able to appreciate this fact? So, I have pages on my logical address space, I have page frames on my physical address space, and anything that I move from the disk to the RAM, it will be in terms of blocks. In this case, this block is called a page, and I will be moving, if at all the logical address space wants to talk to the physical address space, it is the only thing that it can directly talk to, then basically it is going to send pages of data, and those pages can come and sit in these page frames. Are you able to follow? Now, so how many, so let us go to the next part. Zero to 2 power 32 minus 1 is the address space, the logical address space. In addition, I will have something called a translator, okay, which will basically translate, and then I will have something called, it cannot be as big as this. This is the physical address space. Okay. Now what will happen is, let me say this is page number 1, 0, 1, 2, 3. Like that it goes. Now what I do is that for every page I need to know, I need to translate for every page here. So let us assume that each page is of size 2 power 12 bytes. This is 4096 bytes. Each page is of size 2 power 12 bytes. And for every page I should know whether that page is still in the logical address space or it is moved into the physical address space. If it has moved into the physical address space, I should know which physical address space or which page frame. So this will also have page frames. So for every page in the logical address space, I need to know if at all it is loaded into the physical address space. If in case it is loaded, I should know which exactly is the page frame on which it is loaded. Okay, are you able to follow? Yes or no? So let us say, so how many entries should I have here? How many entries should I have?
2 power 20.
2 power 20. Why so much time for this? Okay. So I have 2 power 12, each is 2 power 12, total is 2 power 32. So I need to have 2 power 20 entries, right? And each, what is 2 power 20 is 1 megabyte, right? Mega entries. And what should this tell you? It should tell me which page frame it is loaded. Okay. So how many bytes I need for specifying the page frames? So this is a 32 bit. No, I should tell which page frame it is loaded. So I may, for every page I should know which page frame, and that page frame I may tell it as a beginning address of something. Address of this page frame, so it will start, right. So that address would be, again I need 32 bits because I need to start the starting address of these page frames. Suppose I am storing like this. So what is the total storage involved? 4 bytes, right. 4 bytes is 2 power 2. So I need 2 power 22 bytes for this translation. That will be something like 4 MB. 2 power 20 is 1 MB, 4 MB. So the size of this translator table itself will be 4 MB. Correct? The size of this translator table itself will be 4 MB. In which I will, by using that 4 MB, what I can say whether a particular page is in the memory or not, and if it is in the memory, where in that memory. This I can address by this. Okay. Right. Now somebody should tell me where this table is. This table will be loaded into memory itself. Right. Somebody should tell me where this table is, which address it is available. Then only I can go and update these values. Correct? Okay. So I have some register. Let me call it as page register. This page register will tell me where this translating table starts. Now suppose I am generating a logical address which is 32 bit in size. I will use the first 20 bits to go into this table, because this is 2 power 20, right, it will be 20 bits. So I will use the first 20 bits to go to index into this table. So what I will do, I will take the first 20 bits, add it with page register, and then go into this entry, correct. In this entry what I will have is whether this page is loaded or not. I will have information whether this page is loaded or not. If this page is loaded, then it will give me the start address of that page. To that start address I can add these 12 bits, the least significant bits, and that will give me my actual address. So if I want to access a data, so I am generating a 32 bit address that will be spawning across this logic address space. So that will be in some page number which is given by the first 20 bits, because each page is 2 power 12 bit addressable, like 2 power 12. So the first 20 bits will identify what that page is, correct. So I use that 20 bits as an index to this page register plus that 20 bits will give me the index where I can go and look at whether the page is already loaded into your physical address space. If it is loaded, then I have to, if it is loaded, then I take the remaining 12 bits here, add it to the this base address, and I can get the actual address. If it is not loaded, then I have to go and load it from the logical address space into the physical address space. If it is not loaded, then the processor will create something called a page fault. When the processor creates a page fault because it is not available here, then I go and bring that page and load it into this memory and adjust that entry so that it points to it. Okay. So what we have seen today is a very simple setup wherein I am having a logical address space which is 4 gigabyte in size. I am having a translator, and then I have a physical address space which is some very less value. So in the logical address space, whenever a program generates a memory request, right, that memory request essentially is sent to the logical address space. It is generated from the logical address space. So I get that 32 bit, I take those 20 bits to index into a table which is a translator table. The starting entry of the translator table is stored in some page register. I just add that many thing and index into this table, and this table will tell me whether the page I am looking for is available or not, and if it is available, where it is available. If it is not available, then the architecture will raise a page fault which will go and fetch that relevant portion from a physical memory, from the logical address space into this physical address. Okay. Do you got a feeling? Now the biggest thorn in the flesh for this is that I am wasting 4 megabytes of data just for getting paging. Can I do something better? That is also there. Every time I am enabling paging in this scheme, if this is the scheme that is final, then what is I need 4 MB of space just to store page translation thing, which is not acceptable. We can do something much better than this. So this is the notion of virtual memory. We will continue this in Monday's class again on how these different aspects are taken care of. But this, in essence, this is the import of virtual memory, okay, right, and a translation wherein I go and say, you give me as much code you want, I will execute it with as less memory I. Okay. Right. We will further deliberate on these topics.